Hi students, this is P. Eswari, working as Assistant Professor in Vignan Institute of Engineering for Women. Today I would like to give a lecture on Bernoulli's differential equation. In the last lecture, I already gave about the information about linear differential equations. Now this is Bernoulli's differential equations is a continuation of linear differential equations. First let us see the definition of Bernoulli's differential equation. So this is a Bernoulli's equation, an equation of the form dy by dx plus p into y is equal to q into y power n is called a Bernoulli's equation. First let us see why we need to discuss about Bernoulli's equation in the continuation of linear equations. Let me explain with an example. So consider an equation dy by dx plus 2xy is equal to 3x square. This is a linear equation, right? Now, again consider an equation dy by dx plus 2xy is equal to 3x square into y square. There is a slight difference between these two equations. First, let us observe the first term. The first term is same for the equation and the second term is also same for the equation. Now coming to the third one, in the third one we have an extra term on the right hand side as a multiple of 3x square, that is y square, right? The difference between these two is the term y square. So, an extra dependent variable y, if present on the right hand side part, that equation comes under Bernoulli's differential equation in y. So, if you observe, this is an extra term on the right hand side y square. Now, we have to see the working procedure of Bernoulli's differential equation, right? So, this Bernoulli's differential equation can be solved by converting it into a linear differential equation. Now, let us see the working procedure of Bernoulli's differential equation. So, working rule to find the solution of Bernoulli's differential equation. So, we already discussed this is the general form of Bernoulli's equation dy by dx plus p into y is equal to q into y power n, where p and q both are functions of x and y power n is the extra term that we need to eliminate to convert this equation into a linear equation. For that, what we have to do? We have to divide this entire equation with this extra term y power n. If we divide the equation with y power n, let us observe 1 by y power n dy by dx plus py by y power n is equal to q y power n by y power n. So, we are dividing the entire equation with y power n. So, what happens? If it goes to the numerator, it becomes y power minus n, right? Y power minus n dy by dx plus p into, here the power is 1, right? Y power 1 by y power n is nothing but y power 1 minus n, that is here, is equal to, if y power n cancel, we have q. So, we got this equation, right? Here we have to take a substitution. What is the main important substitution in the Bernoulli's equation is, we have to take the term y power minus 1 as t to convert this equation into linear. So, let us take y power 1 minus n is t. So, differentiate with respect to x. What happens if we differentiate this with respect to x? It is in the form of x power n, right? So, the formula for d by dx of x power n is n into x power n minus 1. So, let us apply this formula to this one, y power 1 minus n. So, what happens? 1 minus n into y power 1 minus n minus 1. Because we are differentiating with respect to x, it becomes dy by dx is equal to, again on the right hand side we are differentiating with respect to x, it becomes dt by dx. So, it becomes minus 1 plus 1 cancel. So, we have here 1 minus n y power minus n dy by dx is equal to dt by dx. So, after this y power minus n dy by dx becomes 1 by 1 minus n. When it comes to the right hand side, 1 by 1 minus n dt by dx. So, what we need to do? We have to substitute this y power 1 minus n equal to t and y power minus n dy by dx equal to 1 by 1 minus n dt by dx, these two in the equation number 1. If we substitute in the equation number 1, it becomes y power minus n dy by dx, which is nothing but 1 by 1 minus n dt by dx plus p into what is y power 1 minus n, which is t. So in the place of y power 1 minus n, write t is equal to q. So now we have to convert this equation into a linear. So if you observe this equation, this is like a linear equation, but we have here an extra term, right? 1 by 1 minus n is an extra term. So to eliminate this, we have to multiply this with 1 minus n. Multiply this entire equation with 1 minus n. We get dt by dx plus p into 1 minus n into t is equal to q into 1 minus n. If you observe the last equation, it is clearly a linear differential equation in variable t. Okay, so this is a linear equation in t which can be easily solved, as I already discussed in the last lecture, the solution of linear differential equation. Now let me explain the Bernoulli's differential equation with the example. So let us have a look on the first example. So this is the first example. Solve x into dy by dx plus y is equal to x cube into y power 6. First we need to convert the given equation into a Bernoulli's differential equation. First observe the first term. If we look at the first term, we have the extra term here x. So we need to divide the entire equation with x to get some general form. So let us divide the equation with x. Dy by dx plus y by x is equal to x cube y power 6 by x. If we divide, we get x cube and x cancel. So we have x square into y power 6. So if you observe this equation, it is a Bernoulli's equation, right? Dy by dx plus p of x into y is equal to q into y power n. What is y power n here? Y power 6. So our extra term here is y power 6. So we have, what is the working procedure of Bernoulli's equation? We have to divide the entire equation with that extra term on the right hand side, which is y power 6. So divide the equation with y power 6, we get, if we divide the equation with y power 6, we get 1 by y power 6 dy by dx plus y by x into y power 6 is equal to x square into y power 6 by y power 6. So on dividing this, we get, if it goes to the numerator, it becomes y power minus 6 dy by dx. When y and y cancel, we have here 1 by y power 5. When it goes to the numerator, it becomes y power minus 5 into 1 by x. When y power 6 and y power 6 cancel, we have x square. So this is the equation after division. Now what we have to assumption as t. So that is main important thing. We have to take the middle term y power minus 5 as t to convert this equation into a linear equation. So let us take y power minus 5 as t. So if we observe, we have to differentiate this with respect to x. So if we observe, it is like a formula d by dx of x power n, which is n into x power n minus 1. So observe here, x power n is nothing but minus 5, x is nothing but 5. So minus 5 into y power minus 5 minus 1, because we are differentiating with respect to x, we have dy by dx is equal to, on the right hand side part also we are differentiating with respect to x, we are getting dt by dx. This becomes minus 5 y power minus 5 minus 1 dy minus 6 dy by dx is equal to dt by dx. So on dividing this with minus 5, so we are getting y power minus 6 dy by dx equal to, when it goes to the right hand side part, it becomes minus 1 by 5 dt by dx. Now what we have to do? We have to substitute this y power minus 5 equal to t and y power minus 6 dy by dx equal to minus 1 by 5 dt by dx in the above equation number 1. Then it becomes, so the first term when we substitute, it becomes minus 1 by 5 dt by dx here plus y power minus 5 is t into 1 by x is equal to x square. So if we observe this equation, it is like a linear equation, right? But here we have an extra term. So what is our extra term? So here we have an extra term minus 1 by 5. So we have to multiply with minus 5 to eliminate this minus 1 by 5. So let us multiply this equation with minus 5. It becomes dt by dx minus 5 by x into t is equal to minus 5x square, which is a linear equation, right? But it is a linear equation in which variable? It is a linear equation in the variable t, right? This is a dependent variable, so it is a linear in t. Now what is the integrating factor? Now we have to go into the working procedure of linear differential equation. The integrating factor is e power integral p dx, which is e power integral. What is our p here? Compare this with linear, dy by dx plus p of x into y is equal to q of x. So this is our p and this is our q. So e power integral, so p is minus 5 by x dx. What is the integration for this? E power minus 5 integral 1 by x is log x, that is e power log x power minus 5, e and log cancel, we have x power minus 5, x power minus 5 and goes to the denominator, it becomes 1 by x power 5, which is the integrating factor. Now the general solution is, because it is a linear differential equation in t, the general solution becomes t into integrating factor integral q into integrating factor into dx plus c. So t into our integrating factor is 1 by x power 5 is equal to integral q. What is our q? It is minus 5x square into integrating factor is 1 by x power 5 dx plus c. When x square and x power 5 cancel, we have here minus 5 1 by x cube. So minus 5 take outside, x power minus 3. When it goes to the numerator, it becomes x power minus 3 dx. So what is the integration for this? It is like x power n plus 1 by n plus 1, which is x power minus 2 by minus 2. Minus by minus plus 5 by 2 into, when it goes to the denominator, it becomes x square, which is 5 by 2x square plus c. So at the end, we have to substitute what is t. What is our assumption? Our t is y power minus 5. Substitute that here. So it becomes y power minus 5 and goes to the denominator, it becomes 1 by y power 5 into 1 by x power 5 is equal to 5 by 2x square plus c, which is our general solution. Next, so far we have discussed in the example 1 the Bernoulli's differential equation in y. Now let us discuss the Bernoulli's differential equation in x. So if we observe this equation, it is dx by dy plus px equal to q into x power n. What is the dependent variable here? So x is the dependent variable. If we see, so the extra term of x is present on the right hand side part. So it is a Bernoulli's differential equation in x. If there is no x here, we don't have any problem. It is a linear differential equation. We can solve there easily. But here we have an extra term x power n. So it is a Bernoulli's differential equation in x. The working procedure is same as that of Bernoulli in y. So I am directly explaining with the problem of Bernoulli's equation in x. So let us see the example. Solve dy by dx into x square y cube plus xy is equal to 1. So by looking at the question, we can't decide whether it is a linear or Bernoulli. First we have to write what is the dy by dx from the question. So first let us write dy by dx from the question. It becomes dy by dx equal to 1 by x square into y cube plus xy. Here also we can't decide whether it is a which equation. So let us take a reciprocal of this equation. Dx by dy is equal to x square y cube plus xy. So let us bring this xy term to the left hand side part to get the general form. So dx by dy minus xy is equal to x square y cube. Okay, so we are getting this general form. Now observe this equation. Here we have a dependent variable x on the right hand side also we have the x. What is the extra term here? What is the extra term here? Here we have an extra term x square. So here we have an extra term dx by dy, right? Here we have an extra term x square. So we have to divide the entire equation with x square to get converted the equation into a linear differential equation. So let us divide the equation with x square. It becomes 1 by x square dx by dy minus xy by x square is equal to x square y cube by x square. So after division, when x square goes to numerator, it becomes x power minus 2 dx by dy. When x and x cancel, we have x power 1. When goes to the numerator, x power minus 1 into y. When x square cancel, it becomes y cube. Now we have to take a substitution to get converted into a linear. Every time the middle term is taken should be a substitution. What is the middle term here? X power minus 1, that should be taken as t. So after this, what is the next step? Differentiate with respect to y. Here we have to differentiate the entire equation with respect to y, because here we have, observe here, we have dx by dy. So we should differentiate with respect to y. When dy by dx is there, we have to differentiate with respect to x. So when differentiate with respect to y, it is also like x power n. The formula is n into x power n minus 1. So it becomes minus 1 x power n minus 1 minus 1 minus 1. Because we are differentiating with respect to y, it becomes dx by dy is equal to, on the right hand side, dt by dy. So it becomes minus 1 x power minus 2 dx by dy is equal to dt by dy. So when take this minus 1 to the right hand side, it becomes x power minus 2 dx by dy equal to minus dt by dy. Now what we have to do? We have to make a substitution. We have to substitute this x power minus 1 and this x power minus 2 dx by dy in the equation number 1. Then it becomes x power minus 2 dx by dy is equal to minus dt by dy. The first part. Next minus x power minus 1. What is our x power minus 1? T. T into y is equal to y cube. Now just change the symbols to get converted this into a linear equation. If we change the symbols, it becomes dt by dy plus ty is equal to minus y cube, which is a linear in t, right? Here we have a variable, dependent variable t, no? So it is a linear equation in t. Then what is the integrating factor? First we have to take what is p. So here this is p and this is q, right? Next, integrating factor, the procedure of linear equation, e power integral p dy. So e power integral, what is our p here? Y into dy. So e power, it is a y power 1. It is like y power 1. So a formula is x power n plus 1 by n plus 1. So e power y square by 2. That is the integrating factor. Next, the general solution. Because it is a linear in t, the general solution starts with t, right? T into integrating factor, integral q into integrating factor dy plus c. So t into our integrating factor is e power y square by 2 is equal to our q. What is our q on the right hand side part? Minus y cube. Our integrating factor is e power y square by 2 into dy plus c. Now let us see the procedure of solving that. So here, look at here, this is the integration we have to solve. For this, we don't have a direct formula for that. So we have to take this y square by 2 as u. Because we already used t, we have to take some other variable. So y square by 2 is equal to u. Then y square equal to 2u. Next, differentiate this. 2y into dy is equal to 2 into du. That is y into dy is equal to du. Now substitute here on the right hand side part. Minus, take minus outside. This y cube, write this y cube as y square into y. E power y square by 2 into dy plus c. So it becomes minus, what is y square? Y square is nothing but 2u. Y into dy. What is y into dy? Du. E power y square by 2. What is our y square by 2? U. So take this minus 2 outside. U e power u du. So this is integration by parts. So after solving this in integration by parts, you can remember like a formula. So e power u into u minus 1. So after solving in by parts, we get this formula. So this is minus 2 into e power u. What is our u? Our u is y square by 2. Y square by 2 into again u is y square by 2 minus 1 plus c. Our left hand side part, t into e power y square by 2. We know what is t. What is t from our substitution? T is x power minus 1, right? So t is x power minus 1 e power y square by 2. So when x power minus 1 goes to the denominator, it becomes x power plus 1. So this is Bernoulli's differential equation in x. Now, so in the next class, we can discuss about differential equations reducible to linear by substitution. I think you have the idea how to solve the Bernoulli's in x and Bernoulli's in y. In my next lecture, I will give the how to solve differential equation in linear by substitution. Thank you, students.